My name is Dmitry. I'm a software engineer, and I've been working at Facebook for a bit more than 2 years. I work at Test Info team. And yeah, by the way, who wants to have lunch right now? I think you're lying, guys. You want to have lunch, everybody. And yeah, sorry for that, for being the last one before lunch, but this is the last mental effort. Concentrate. It is not be. It's not going to be super easy talk. So please, it's last effort. Yeah, and we are based in London. And what our team is doing, it's basically 3 things. The first is we supply frameworks for writing tests. Then we actually run those tests. And finally, when the tests are executed, we need to show the results to developers or to testers. So we are responsible for signal. And what I'll be talking about is, boom, is the second part, which is the test execution. And here's what I'll be talking about. So first of all, I'll set some context about how do we actually write code at Facebook. And we are a big company. We have a rich set of products and tools. It's not only Facebook. It's also like Instagram, Messenger, Workplace, Oculus, name it. And for that, we have really astonishing code base. And what is scaring, it keeps quickly growing. And the reason I'll mention about it is the way we approach our continuous integration influence the way we approach testing. The second, in order to deploy that big amount of code, we obviously need tests, and we need a lot of them. And I'll introduce some sort of test classification, like type of tests, but from a little bit specific perspective, namely what makes a difference from scalability point of view. And finally, the core part of the talk sounds like relatively easy, which test to run and when. And the word relevant here is for a reason. It refers to the fact that we actually can't afford to run everything as often as we want. And I'll show you why is it the case and how do we try to tackle this. So let's go. But before we start, I was told that the level of the talk is intermediate, so it's not simple. And I'm not going to ruin the expectations, so here's a brain teaser for you guys and folks. Yeah. So the brain teaser is called wine poison problem. It's the following problem. You have exactly 1,000 barrels of wine, and you know for sure that exactly 1 barrel is poisoned. And you really want to find out which one is that. And the toxic agent can harm a human, but the scientists discovered that thankfully it reacts quite the reverse to the elephant. If you feed it to the elephant will get excited and happy for a while, which is great, but we have a problem here. The problem is the first symptoms occur in 1 day. And unfortunately, 1 day is all we have. So the question of this brain teaser is, how many elephants do we need to identify? So raise your hands who have heard of this before. Nobody, no geeks. Oh, we have somebody. We have 2 math geeks. Who knows the answer? Oh, okay, a friend of mine, of course. Yeah, so, and while you're thinking, and let me actually start. So, continuous integration. As I mentioned, the challenge here is to manage our huge code base and don't get lost. So this might sound like a little bit counterintuitive or maybe even mind-blowing, but it turns out that small number of large repositories is actually easier to scale than the reverse, the big number of smaller repositories, at least in Facebook environment. So what our source control team is doing is they trying to make it possible to actually have one gigantic, huge monorepo. We are not fully there yet, but we are quite close. And what are exact benefits of having monorepo? Why is it not a crazy idea? And there are quite a few of them. Like the first one is a little bit hand-wavy. but their core idea is it's ultimately very simple mental model. So at any point of time, you know exactly the state of your system. And it simplifies a lot of things, including testing. To provide more concrete things, it simplifies sharing the code. Libraries do not need to be copy-pasted and duplicated, and we basically don't have version hell problem. And this would be a big problem given our scale. And what is also cool, that libraries can be updated with the code that using this library simultaneously. But my favorite one is that guy is something that allows us to keep our code base modern and complying with our up-to-date quality standards by simplifying en masse changes. And this is one of the reasons I love working at this company. And let's consider the example. So you probably maybe know that Facebook.com backend historically was written in PHP, which is sort of dynamic language. And since then, what we did, we figured out that long-term strategy should be safety and sustainability. And what we did since 2011 or something like that, we've been developing a hack language. And this hack language was initially backward compatible with PHP. But now, our code base has really very little common with PHP. The code is written in modern, type-safe, object-oriented language. And what is super important, it has async await. And it has a lot of other nice features. And for me, it really feels like a completely different language. And we did the same with JavaScript. And what's really cool is that new features and improvements are still being added regularly, and they come along with automatic code migrations. And this is really cool to observe. And so what do we have? We have a rapidly changing code base, and the language evolves on the fly. So the problem is how we actually synchronize the change between developers. It sounds like a challenge, and merging might become a nightmare. So this is how it works. Who knows what is it? It's a trunk. Have you heard the controversial talk from Thierry about feature branches considered evil? Who of you have heard of it? Wasn't this talk? Yeah. So, well, we don't use them either. We do agree that they are sort of too sluggish for our scale. And what we do, we use feature toggles. What feature toggle is basically a condition in the code that contains both versions, the feature you are developing and the previous one, and we can remotely toggle this feature, and this will take effect on all Facebook servers in seconds. So what we do, we commit right onto trunk. And we prefer to commit very frequently and split changes to small manageable chunks. And the idea is each commit becomes essentially a non-event. So how do programmers work? If you're a programmer, you check out the current trunk, you write some code and hopefully some tests, you submit them for code review, you wait for feedback, you address comments, and then finally you click a button, and our continuous integration system will asynchronously commit your change and merge it to trunk. So, and it's also important to say that you don't need to wait until your code is reviewed. You're not blocked because you can specify that your two changes depend on each other, and you can actually proceed coding straight ahead. And so the question is, this sounds scary. A lot of developers, thousands of them, are working on trunk. What if it's broken? And this finally brings us to testing. And somebody needs to protect trunk. And this is, in the rest of the talk, I will talk about how we do it. So let me describe the first system that can be called retroactive protection. So what we do, we periodically run full set of our tests post-commit on the current version of trunk. How often do we do it? It depends on the test's importance, and if the test is really critical, for instance, it can block the release, it might be as often as each 5 minutes. For less often important tests, it can be like several times per hour. And what we do after we're sure that the test is broken, we need to notify the developer. or tester. And then finally, the test needs to be fixed, or the bug needs to be fixed, or it could be as easily as just revert the offending commit. And there is something that is lacking in this nice picture. I didn't say whom to notify and how do we actually find the commit. And this brings up to a very important, crucial system that I will mention over and over again in this talk. So this we call blame. And the idea is it's popularly named as blame. It can use divide and conquer technique, divide by half, and basically find when was the commit that actually breaks tests. And why is it super important? I think about the blame as productivity catalyst. It dramatically accelerates diagnostic. So, because usually the best way to understand what happened with the tests is actually to look at the commit that broke it. It's easier than trying to debug it. Also, the right responsible person is not the test owner, it's actually the person who broke these tests. And also, finally, and fastest, easiest way, as I said, is just to revert the commit. And note the last line in this slide. Some tests, especially black box or UI tests, might depend not on the code. It might depend on some external factors like currently activated feature toggles. So what we also have, we have a blame system that allows us to find which toggles are responsible for breakage and revert them back. So this is still not super cool because this is still about repairing the broken trunk. And what's really cool is obviously proactive protection. So this is pre-commit checks. When you submit your code for the code review, we run some tests. And I will tell about this. But before that, a little bit, let's sort out terminology. So the problem is, the thing that you submit on code review, different system called differently. It's either called pull request or merge request, and it might be confusing. Also, there is a company that calls it change list. And also, there is one more system that goes in two ways, either it's change or patch set. Also, there is a company that calls submission, and revision, and review request, or just review, or topic. Or we can use abbreviation. PR is very popularly used, or CL. And and if you have 14 competing standards, what I'm going to do, of course, I'm going to clean this mess up and introduce a nice new shiny standard, which the word that we use at Facebook, which is div. But it still means absolutely the same. I'm just used to this word, so it will be easier for me to use. So pre-commit checks. So why are they super cool? First of all, obviously they keep trunk green. That's the main goal. But what is even more cool, they're extremely actionable. And what do I mean by that? In post-commit world, what do we have? If you know the commit, you still need at least to revert it. And it might be actually not that easy. Or if you don't know the commit, you need to fix the bug, which is also hard. But in pre-commit, the proper action is as easy as just, please, can you not commit this? It's much easier. And our researchers indeed show that this indeed improves consistently the fix rate. I would also say, if after we had this pre-commit system, we found that it improves developer efficiency to a big margin. So developers, reviewers don't need to concentrate on finding actually bugs. They can think about high-level things. And if you're a developer, you can afford more crazy refactorings maybe. And this, unfortunately, doesn't come for free. And the reason, again, is our scale. So, and this boils down to these two guys. The first one, number of tests, which is really a lot. And we have the same for post-commit system. But in pre-commit checks, we also have a big number of divs. And with thousands of developers, we have many thousands of divs per day. And if the scale here is essentially a multiplication of those two guys. So we have two big numbers. We need to multiply both of them. And both of them, as you can see, quickly growing. So this is a problem. So actually, which checks to run? And we have a lot of different sort of checks. Some of them are not even tests. And I could not resist to show this picture. Probably you all saw this before. And this suggests that if you're a tester or developer, your attention should be naturally shifted toward the bottom of this shape. Because here's an easy test. They're easy to act on, easy to write, easy to debug. But as somebody who works on infra, my attention is shifted backwards. It's shifted to the top of this pyramid, because this is where the scaling problem comes from. And this is, let me provide a little bit classification of those tests. So this is what makes different from scalability point of view. First of all, we have unit tests, and they are practically a dream for people like me. They are really fast, really easy to debug, but what's most important, they have very granular surface area, which means that in most cases, you actually don't need to run them because they have nothing to do with the change. They're testing something else. And then there comes like big amorphic gray area of sort of unit, but unit-ish tests, and which have a lot of, might have a lot of dependencies, and everything is getting slightly harder, especially not running them. And then the interesting difference happens when the test wants to go beyond the box and do some network requests. What we immediately have, we have a reliability drop because network is not reliable. And as an extreme case of cross-host tests is like famous black box tests, UI tests, for instance. And the biggest problem with them is not only the resources, computational resources that they require, is that the code under tests and the code of the test are completely separated. There is literally nothing common in them. For instance, the UI test code can say, find this screen, find this button, click this button. And it literally has nothing common with the code itself. And it complicates a lot of things, as we will know. So after we talked about all these problems, which checks to run? We still want to run all of them because software is hard and there are a lot of things we want to be protected from. So let's do it. So how to scale it? So we have a big formula from two big numbers and how to actually scale it. So we have two ways, right? We can either pretend, do something that they sort of, we have less of tests or less of diffs, less of pull requests. And let's start from the first one. So this is called test selection problem. The problem is how to find the test which to execute. And this is a really, really big area of research, and there are a lot of papers around there. But I'm not going to touch it deeply. I literally spent 2 slides on them. And the reason is, first of all, I wanted to share some less orthodox approach. And the second is my colleagues are currently preparing some scientific papers with a lot of meaty details, and they asked me, Dmitry, can you not spoil? And but the idea is we first have coverage. And the static case is super trivial and works very well for unit tests. The idea is, as I already told you, if the change request, the diff, doesn't touch any model that the test depends on, why would we run the test? We shouldn't. And this is simple but crucial optimization. But sometimes this information is not granular enough. Or maybe we have a test that doesn't want to declare all the dependencies. As again, as an extreme case, recall what I just said about black box UI tests. The code under test and the test completely separated, so the coverage just doesn't work. So what we can do, we still can have dynamic coverage. So how does it work? Periodically, we run the full suite of tests, but in special mode. In this special mode, our servers actually know that they are executed inside the tests. And they declare which models did they execute during the tests. And for instance, we have this for both server-side part in WebDriver tests and for JavaScript. And we have the same system for feature toggles. The test can know which toggles are being checked during the tests. And then, if somebody wants to change the feature toggle, we can execute those tests that we think can be broken. Yeah. Then predictive test selection. So this is again huge area, but ultimately the idea is, if you think about it, it's the classical machine learning problem. You have a diff, you have a test, and you have some diff features, you have some test features, and you maybe have some diff plus test features. Example of a diff feature is number of lines of code. Example of diff plus test feature is how many models are between the test and the diff in the dependency graph. And this is actually a highly predictive feature. And again, I'm not going to share all the details, but what's important to say, it's a game changer. It works very well, especially for non-black box tests. For black box tests, we again have a problem because the most predictive feature don't work for the same reason I told before. Yeah, so it's actually all about the first approach, and the rest of the talk will be about the second approach. How do we reduce number of diffs effectively? Yeah. So this is a core idea, and this is the horizontal line is our trunk, is our main line, and the arrows here is diffs that are currently pending review. And as you can see, they are routed from different points because developers rebase in different points of time, and also they can have dependencies on each other. So the idea is actually very simple. Let's do the following. Let's linearize them and rebase onto trunk temporarily. And so we have a virtual trunk, and we can do this trick regularly. So we batch those diffs together, and then what we can do, we can run a lot of checks against this. And imagine that we have those 10 diffs in the batch, and we run 100 of tests, and 97 of them passed. That's a great news, right? It means that neither of those 97 tests broke. All these diffs are clean, but some of those guys broke those 3 tests, and we need to find out which. And for that, we have something that I already mentioned, blame, very similar technique. This is the main idea of our optimization. So, how does it scale? And in order to understand the scale better, I like the following metaphor. Let's look at it from slightly, this is actually blaming diffs here. Looks from it from slightly different perspective. And I really hope some of you will understand what's my favorite movie. So this line represents time, and the future is on the right. And imagine that at some point of time, a very disruptive event happened. It disturbed time continuum, and for some reason, our code review system disappeared. So what people started to do, they started to commit right onto trunk without any test and code review. And this event would obviously create an alternate reality. And that would be a much less nicer place to live in than our reality, because a lot of bugs will be. And, but know that in this alternate reality, we would still have the post-commit retroactive system that I just mentioned. It would still run post-commit checks, still run blame, and still find which commits are bad. So what we are essentially doing, we are building sort of time machine that allows us to simulate this future that didn't exist, but it would exist if those diffs were committed right now. So who knows what's my favorite movie now? Yes, somebody knows it. Cool. Yeah, because when I did dry run in my team, nobody knew this. And I was like, guys, are you kidding? This is a very popular movie. And like, what? No, we don't know. Yeah. So from this point of view, it's obvious that order of scale is essentially the same as for our post-commit system. But it doesn't mean that they are absolutely equal. They have very different important trade-offs, and let's consider some of them. Again, we compare pre-commit, post-commit, and batching by pre-commit. So the first is time to signal. So what actually happens if we delay post-commit blame? It's a pity, it's a big shame. It means the test will be fixed later, not sooner, and the release might be delayed. But in budget runs, it's actually 0 to 1 change. The diff will either be committed or not. The bug either will be in trunk or not. That's why it's really important to do it faster. And we're sort of racing against the developers. Developers want to commit really fast. They want to move on. And we want to say, like, calm down, let's let's check everything. And the second is, we have code review system for reason, and we don't expect super many broken changes in trunk. But a div could be experimental, for instance. And I will touch about it later on. And this is just the fact that when we create the batch itself, we don't create any batch in post-commit runs. Everything is already committed. But we need to think about a lot of details, like how to make it fast, reliable, how do we handle merge conflicts, how do we handle dependencies, and so on. And there are two good news that help us to scale. Oops. How did I do it? And the first is in post-commit world, the goal is to get every test fixed because they're already broken. And we want to blame all the failures. But in pre-commit worlds, the goal is just to stop the div to be committed. So it's enough to find any test that is bad. And this optimization helps us a lot, as we will see. And finally, there is a sad philosophical fact that I'm not happy from. It's that we can't control our past. And those commits already happened in post-commit world. But we can influence our future, and we can play around with which divs go to which batch in pre-commit case. And we'll talk about it a little bit. So this is like the main trick that allows us to scale. And if we batch divs often enough, if it's actually rare, when we have several divs breaking tests. In fact, in many cases, all tests will pass because neither divs are bad. And what is even more, even if quite a few tests are broken, it's rare when there are many different divs that break it. And what these facts allow us, this allows us to speed up the blame dramatically. Instead of traditional binary search, slow blame, what we can do, we can recheck more suspicious failures on suspected change simultaneously. So again, we don't need to recheck everything because only a small amount of tests would fail. And we can do it in parallel for all divs in batch, and this will be fast and reliable. And this works really well until it doesn't work. And the cases when it doesn't work, we call it batch poisoning. An example is still some div broke the whole batch, broke all of tests. Or for instance, some div broke the compilation and the code doesn't compile if we talk about the code that compiles, not hack and not JavaScript. And in this case, we are in problem, and there are two ways to solve this quickly, like proactive. It's again sanity checks. The idea is, what if we quickly figure out, hey, this div is suspicious, let's not put it in batch at all. And the example of sanity checks is, again, we can quickly try to compile this div, or we can quickly run some predictable unit tests. And if you don't like it, reject it. And it doesn't help always, but it's a huge win. And when it doesn't help, we still have broken poisoned batch. Then let's do retroactive thing. Let's reshape the batch. For instance, split into the halves and repeat the procedure. This might hurt latency, but this is the only thing that we can do. And this is basically almost all. And these batching use cases that we use when they're most important, it's again black box, mobile tests or UI browser tests. Then batching is actually the only thing that we can do. And we also use it for compilation verification for especially expensive software, computation expensive that we really want to save. And I promise you that's a last mental effort, but you need to really focus. So I'm going to talk about compilation verification in a little bit more detail, because this is actually all I said about how do we optimize batching doesn't work in this case. And this is why. This is all tricks I just talked about, and let's see that they don't work. So instead of many small checks, what we have in compilation case, the batch either compiles or it doesn't compile. And why is it bad? Because as I said, normally we can recheck in parallel because most checks will pass. But what we have, if we have a bunch of divs and it doesn't compile, it means that some div broke it, but we still don't know which one. And it's essentially the poison case that I just talked. Okay, we have two ways to solve poisoning, sanity check and reshaping. Let's sanity check it, but actually compilation is sort of sanity check itself, right? So it's hard to come up with good predictable things that we can understand. Oh, this diff doesn't compile. And reshaping the batch retroactively also, it will work, but again, the latency will be really bad. And like absolutely final idea is, what if we combine proactive and reshaping? And this finally brings up to the brain teaser from the beginning of the talk. So the barrels are actually stand for diffs. And the toxic barrel is actually a poisoned diff. And the elephants, what do they stand for? So I remember that we have elephants, we need to feed them wine and identify the poisoned bottle. And the elephants are actually test runs on the batches. So the idea is each elephant will be given a unique mixture of diffs or wine barrels. And this is how it works. Let's consider the example. So we have thousands of barrels, and let's encode them into binary system. For instance, this is barrel number 6762, it gives that number. And let's make some batches. Each elephant will be fed approximately half of all barrels. The first batch will contain all barrels with leftmost bit equal to 1. And this is numbers for those who are interested. And we will feed this guy to the first elephant. And the second batch is all diffs with the second bit equal to 1. And we will feed this to second elephant, and so on. So the last elephant will essentially have all bottles, barrels with numbers, 1, 2, 3, 5, etc. So now we feed this, and what we do now, we wait for 1 day until the symptom occurs and see what happens. Boom! So those elephants are excited and happy, and this means that those guys got something in their mixture, right? And from them, we can actually decode the encoding of a barrel. This is a solution for the brain teaser, so answer is 10. And this is the example. This is what we have in this case. So we use the same technique, and it helps. And I'm coming to conclusion. At Facebook, we ship code by making frequent, small, code-reviewed commits on top of trunk. We need both pre-commit and post-commit testing to keep trunk in healthy state. Pre-commit testing is harder to scale, especially for tests that require a lot of resources and have big surface area. And we use several techniques to scale pre-commit testing: static and dynamic coverage analysis, machine learning-based test breakage prediction, batching together, etc. And here are those of us who are present here for this conference. Archit, Wojtek, raise your hands. So come say hi and chat with us. And thank you very much for listening.